In our working session, a reminder, if you are the flags, you email your flags to Natalia. You take care of them. Our first one from Mark tell us about fillable contact structure from voice to second. Push the button. Oh, yeah. Now it's red. What's the green? That was okay. I'll just wait. Yeah, not here. Okay, yeah, I'm not working. Okay. Well, thanks a lot for the invitation. It's great to be here. It's enjoyable weather and all. So right, I want to tell you about this work that is all joint work with Scaduto in Alabama. So maybe just start with a bit of background. So I'll talk something about contact topology. So contact tree manifold, that's a tree manifold Y maybe with a subbundle of a tangent bundle. Which is a contact condition is that that's given by the kernel of some one form, say, with a non-degeneracy condition. And so the one way that such things come up is that as sort of suitable boundaries of symplectic or complex manifolds. So these might arise. As sort of boundaries. So, for example, you have a complex manifold, and maybe some kind of suitably convex force function on it. I'm not going to get into detail about what suitably convex means, but then if you look at a sub-level side of that, like the value of C, sub-level set corresponding to C, this is comes to the right definition of suitably convex. This becomes a Stein manifold, and it has a natural contact structure at this boundary. Where the plane field is given by the so this is an ordinal context, so it makes a complex surface. So the boundary is a three manifold, and each three-dimensional tangent plane to the boundary that contains a unique complex line, and that will give you a contact structure under this convexity condition. So this is the only example you might want to have in mind is that maybe it's the four ball. And P is just a radial function. So then that gives you contact structure on the free sphere, a standard contact structure. So this is the strongest version of a fillable contact structure. It's a Stein fillable, but it could be maybe a little more relaxed. And say you have a symplectic manifold. Or manifold. Then you could say it's a strong filling of its boundary. If there's a movable vector field for this symplectic form that's finally the boundary pointing transversely outwards. Open cartoon, and in this case, in the previous case, the Google elected creating work function, so first bullet by the second bullet, and you can get a little more flexible, I suppose, if you want. So you can talk about a refilling. And that's just, you know, why against the boundary C, if all you ask is if it's symplectic performance positive on the non-frequencies. Okay, so these are a few kind of ways that you might get contact structures. All of these kind of contact structures on the right way have the property of being tight. Geometrically interesting properties that you might care about. But in general, you know, if you're given a contact or a three manifold, or even a contact three manifold, not all three manifolds have contact structures that satisfy any of these properties. So they might have tight ones, but not fillable ones, or fillable ones that are fillable in one of these senses, but not others. And in any case, sort of understanding all the intricacies and classification of contact structures like this is big program, I suppose. Okay, in any case, so this is, you know, these are some of the properties that we'll be sort of curious about as we go through the talk. And the other sort of half, that's the first half of the title, fillable contact structures. The other half is about surgery. Let me remind you about that. Another way to sort of change contact structures more directly, I guess, in some sense. So, contact surgery, what does that do? Well, it's sort of translation of ordinary Dane surgery from the smooth category to the contact world. So, you typically want some, you know, maybe surgery, a knot along which you're going to do surgery, and to be have some kind of compatibility with the contact structure. So, for example, Legendrian, if it's tangent line, you've always written that. So in that case, we can have the cartoon local picture of something A and contact lines. Good, so that's to kind of twist around, perhaps. In the case of the Scaduto contact, we're going to give you a branding on a dollar. You choose a general, I guess, a rational number. Then there's a way to produce do a Dane surgery with surgery coefficient R compared to that rating and extend the contact structure across the resulting three manifold. In this kind of context, there's always this back and forth between whether you're talking about framing with respect to the surgery coefficient with respect to contact framing, or with respect to maybe the topological zero framing and such things. So now, try not to get too high up on that. And so then you get maybe a level results you might bias are this context. See, in general, there are some, depending on the values of R, there's some choices involved in this extension of the contact structure. Those are pretty well understood. And in fact, for our purposes, there's sort of the one of us canonical set of choices today. So the right pretend that this is uniquely defined in a given attitude. Okay, so then the story of three manifolds. So any three manifold can be obtained by ordinary interchange surgery along some length of free sphere, and the same thing is true in the contact situation. Any contact manifold by contact surgery on some standard free sphere. And so then you start going back to the first set of points. You start asking what kind of properties of the contact structure, and these ones in particular, can you read off if you have a surgery description of the contact structure? So in particular, what can you say about fillability? It's what I want to focus on. But that's anything as well. So for example, if you do contact surgery using a coefficient here that's negative, then it's at all those properties. So this is more or less ability properties. So I've stated these earlier. After work that's close talks about strictly surgery coefficient -1, and there's some ways to translate any general R surgery into combinations of plus and -1 surgeries, which I guess any guided digits. And then more recently, the fact that negative contact surgery considers tightness as inherently one. On the other hand, it's a positive coefficient. Well, if you do surgery zero contact, builds up and we're twisted. So that case. So if you use positive coefficient, then sort of it's much less clear. It seems that anything can happen. In fact, maybe the way to sort of illustrate that is that the refinement of this fact is that you can actually find any contact structure by surgery on geometry things such that I see by surgery thing. Where all the surgery coefficients are negative except possibly one. So that's what we did. Doing positive surgery, since the negative surgery preserves all the properties and not every positive surgery has those properties. It's the positive surgery can definitely destroy those properties. And since there are contact structures that are, for example, weakly fillable without shine fillable, and things like this have to have positive coefficients in their surgery fusion. So the point is that this sort of last observation leads to the main question that I wanted to try to answer today. So just considering it's a single Legendrian, when is it the case that if you do a positive contact surgery, you get a fillable contact structure? And I mean, I've kind of mentioned radical surgery here in general, but for our purposes, this question, it's enough for us to talk about integer surgery, at least that's what I'm hearing about this. Okay, so that's the question, and maybe I'll just go ahead and give you the answer.
Are you asking that why?
I'm sorry?
Are you asking that why?
But that's part of the theory. Okay, so I guess here we go. So just give you the answer. So we're taking Legendrian, some contact manifold. The theorem says that there's some n like this. Positive integer, such that the result of contact anti-surgery along K is weakly fillable. And let's say weakly filled by some particular symplectically manifold. And for certain reason, I'm going to call them Z prime symplectic structure, omega prime. If and only if the following things happen. So first of all, to answer only that this can only happen if the starting free manifold is fillable. So let's see, it's fillable. And there's some filling of Y containing an embedded symplectic disk. So the picture is this. You have Y with some filling Z omega, have use Legendrian on the boundary, and the condition for there to be a fillable positive surgery is that there should be a symplectic disk inside here, delta, whose boundary is your not. Embedded symplectic disk. Well, okay, so whose boundary, I guess, will be a transverse push off, okay. And moreover, in this situation, this weak filling is prime. You can find the filling of the original Y so that when you say this way, Z omega can be chosen. So that Z prime with this symplectic structure is nothing but to complement the small neighborhood of that disk. Okay. So maybe before I go on this, there's sort of a second. One direction of the implication here uses the term that's worth sort of saying on its own. Sort of stated as here that anytime you got this a disk like this, often sitting in something manifold. With transverse boundary K, you can find a suitable neighborhood of it. So that when you excise that from Z, taking out the neighborhood of your disk, get some smaller form manifold with a restricted symplectic structure. That guy will be refilling with some contact structure on its boundary. And moreover, that contact structure is a team bag contact out of the contact. Let's say a Legendrian approximation of the boundary of the disk. Okay, so this is sort of an answer in some sense to this question, and well, there's sort of a lot of directions you could try to go from there. But for the rest of the talk, I mean, I guess I'm going to just postpone the discussion of the proof. Maybe we'll have time at the end. So what I want to do is sort of unpack and sort of think about consequences and applications, just in the case where you're starting from 3 sphere. But any questions at this point? Yeah.
So that theorem is to replace level by Stein. Then we can start.
By Stein?
Sorry. Just
By Stein. Oh,
so
I don't have an answer to that. Very good.
And how about Stein?
Or I haven't thought of it. So it's sort of more likely to be in reach. But I will say that, right, this is a theorem about weakly fillable. If you're starting with S3, then weakly fillable surgeries are always strongly fillable. So okay, so let's take the proof for now. Let's visualize this. Okay, so a nice thing about S3 is that we know all the symplectic filling to be. So for this theorem, our A is good. I already kind of described to you that S3 is fillable, but it turns out that we know all the fillings of S3. All of them are come up and that every like going in a free sphere. It's equivalent to, like, says, to sort of tells you that if you want to talk about not being S3, I'll have a couple surgery. I don't get A or a transverse split out of it. Bounds and embedded in like a disk in some wall of the whole. Well, more than that, it says that every symplectic filling of such a surgery is equivalent to the complement of such a disk. Well, thanks to say, but one further is because now something like this, where you have a four balls, that one appears in it, and like this, in brackets too. Surgery. So, but the point is that local football is negative definite. So that says that any symplectic filling of positive contact surgery in and out of S3 has to be negative definite. In particular, in that sense, although, well, I'm not going to, so again, this is minor annoyance about the difference between the contact surgery coefficient and the smooth surgery coefficient. But in particular, the underlying example, which is some so the smooth surgery coefficient is the contact surgery coefficient plus that it was the max. That guys are now going to take the format. That's not good. Always happen. So again, that's something. But let's go back to that bit. So kind of looking at this picture, you can just sort of immediate sort of rephrasing this here about having a billable surgery if it only be found in slightly just in a blow up of four balls. This is the four balls of 30 times. You can do some little variations. Actually, it doesn't really matter if you can variate for that. That's sometimes you can blow back down. And that this, go in, now something singular in general, maybe it's a first, or maybe it's greater complicated singularities. But what you can always do is you can always sort of arrange your picture, arrange your situation in such a way, for example, that you can pick a almost complex structure on this blow up so that your disk is homomorphic and also the acceptable spheres are holomorphic. And so then when you flow back down, these singularities are totally holomorphic. Model singularities in a complex curve. So and vice versa, you have a singular disk in the orbital that is locally holomorphic singularity by line on back to the singularity. So sort of is transferred to something. This says that it has a whole surgery. For a transfer push out that allows possibly singular. Like there's four ball, so four varies. So for example, one, you could arrange this to be transferred to the exceptional spheres. And in that case, you know, if you blow down, for example, this gets twice like this, and you blow down this exceptional sphere, then you get up a bit transverse double point. It's several times in an ordinary multiple point strategy. You can then for sure again. So if you like, this is also the same thing, getting down to this orbital, just ordinary positive double points in the areas. Okay. Well, so that connects with something that Tom was talking about yesterday. The definition, I guess. I guess Tom is using the notation B plus and B minus in terms of knot sets. Numbers we call clasp numbers, four-dimensional clasp numbers, and use the letter C, I guess. So so again, we're not in S3. Then C of K is this clasp number is the smallest number of double points in an immersed disk found in K. This is normally immersed, so it has only double point singularities. And you can refine it into sign if you want. C plus and C minus would be the minimum positive number of positive double points inside the disk, and C minus is negative. So the corollary is, you know, in this case, you have a fillable positive surgery. then this class number has to equal four-ball genus K. And the point is that, well, maybe I'll just kind of give you a proof by picture. Found this immersed disk with say just double point singularities. These are holomorphic singularities. They're all positive, so you can resolve symplectically, or you can say smooth. Rather than blowing up, you can smooth them ambiently, and to get a symplectic surface of higher genus. So the kind of picture is supposed to be something like this. So this will be a symplectic surface. With the genus, every time you smooth one of these double points, you replace the normal crossing by an annulus, so you increase the genus by one. So genus is the number of double points. But if you have a symplectic surface in the four-ball, and having some not, then that surface necessarily realizes the four-ball genus of A. So let's just see. On the other hand, you know, this class number is so that is the number of double points you see here is the four-ball genus in this case. On the other hand, you always have to have at least a four-ball genus number of double points just for any smooth surface. For the same reason, as soon as you take any immersed disk, you can smooth it and get some. So C of K is always at least G4 of K. So here's one that realizes G4, and so that's got to be the smallest. And as commented last time, there's, you know, you can say a little more. This disk has only positive double points, and so that tells you something about the C plus and C minus. So, for example, you could look at 7.4. That's it. That's supposed to be drawn so that it's a positive. So 7.4, this is, I think I said it's well, it's a 7 crossing knot, hopefully. That's positive knot. Say again? Oh, maybe. Otherwise, it's sort of 6 crossing knot. So positive number in the sense that it has a diagram for all positive crossing, which is this one. I'm not going to tell you about. All right. And that tells you, for example, that it's strongly quasi-positive. Which we'll come back to if you have what that term means. In fact, word bounds function Lagrangian torus. And moreover, all sufficiently positive contacts are going to be high. Take the suitable confounded representative to start with. But so that for the four-ball genus instead of 4 is 1, while its class number is 2. So I think this maybe was known as a Livingston. Yes, maybe he was talking about a non-member, but OS is too late. Certainly also prove that. So that means that it doesn't have to go on the context degrees. Despite having this sort of roughly copies, of course. Yes, I could mention that there's the difference between this math number and the four-ball is arbitrarily large, which is proved by Chris. Do you want to go and also identified by UMass? That's fine. Let me give you a couple more sort of vanilla examples. Suppose you have a positive braid. So the positive braid closure. So you have the free sphere, which is looking at this. And draw my positive braid, sort of like swirling around with other constant. And there's an algorithm to unmap this thing. I guess you're not more follow it, whatever. It says in particular for this positive braid diagram contains these crossings. To get to braid closure. That's not braid epsilon, where epsilon is exactly n-1 constants. And this epsilon hat closure is not it. So, okay, so you think of those crossing changes as sort of being swept out by some theta, right? So they sort of seduce an annulus and create sphere across I. So now you're not with this. So this is sort of epsilon. Roughly. And this unknotted braid closure with n-1 crossing, if you think of it as a transverse knot, will then something like this. Okay, so you can take that swept out singular annulus. The fact that you're changing positive crossing, you can combine with like a transverse isomorphism that will sweep out the deflecting. And you kind of looks like this. So that tells you that this braid closure counts that is the right inverse of that this gives you one. So you have fillable surgeries. So any positive it's going to be easy to figure out one direction, that is finding something like this and you get it different. But it's the other way around too. So it's another example. Suppose you have a knot that has a space surgery. Then there's lots of stuff you can say about it. For example, one thing you can say is it's according to the screen, then this surgery focus has to be at least twice the segregated. says this particular geometry represented, okay, so there's a benefit number that is, say, the contact framing. That's less than the genus. So that, and put these together, that says that surgery that gives you the lens space, and you realize that it's a contact surgery. The difference between the surgery filtered smooth surgery and the contact framing, in other words, the contact framing is positive. Okay, so that's one thing. So you do kind of positive contact surgery, you end up with a 3-manifold with the lens space and some contact structure. So I think that it's actually tight. So it's I kind of this representative, but it's not. That has a property that you take a specific identity number plus the rotation number. And forget could be -1. And that's because this optical lens space surgery is strongly positive, which follows work with various people. And there's a positive treatment angle, you gotta get back to it. So let's just mention that. And the that any contact surgery with smooth coefficient bigger than 2G this is because once you have this condition, and you also know that when you get this line variant is negative, there's word Marcogola and also a different form of relance in mind that says that they figure word contact class surgeries. Okay, so the point is that the surgery that gives you the contact surgery that gives you the one space, gives you a tight contact space. And the every time I just one space is fillable. That space is so that says that here do not have the space surgery, then it also has fillable contact surgeries. Well, so I just maybe I just erased. If you have a lens space now, then its clasp number has to equal its four-ball genus. I don't know another proof of that fact, so this doesn't say anything about contact topology, but that's what you can prove it. So I noticed that it's a curious thing to see there. Okay. Well, so maybe what I'll do now is take a few minutes. So one thing that we haven't really talked about is like kind of look back at what the main theorem says, is that some positive surgery is fillable, and only if some stuff happens. But it doesn't really say which of the. So let's talk about surgery coefficients. Well, okay. So if you have a fillable surgery, then you found some disc and a blow up on the floor. And then back to the picture over there. And in that case, you want to know which surgery you're talking about. It's not too hard to figure out, really. So, for example, the homology class of that disc, you can think of it as some linear combination of exceptional classes. And the filling of the surgery, or the surgery you get, is depending on the boundary of the disc is. The disc. The disc goes in the boundary. So what's the name of the boundary? Well, think of it as taking the collar of the boundary and attaching the disc to it. Then it becomes clear that the boundary of the result is surgery along A, which is the square something like this. But we're looking at it from the wrong way around, so you actually need to negative. So the boundary of this is C minus the neighborhood is S3E. K, where the surgery coefficient is minus the self intersection of this, and for these guys, square root of -1, or otherwise orthogonal. So this is just giving you the sum of the squares of these ends. Maybe I'll point out that by this trick of making things transverse, blowing out, get multiple points, and smoothing those for the result of the genus. You can express a genus in terms of these kinds too. And what you get is that the four-ball genus has to be, I guess it's a half sum and j times n j minus 4. So one observation is that if you have this disk, if you notice the blow up, there's usually disk is down the blow of the four ball. If you just blow up a smooth point, then you get a new exceptional curve, but depending on what happens to the disk, it's still nice and smooth. And except that its self-intersection drops by 1. So it's negative if the self-intersection goes up by 1. So you get a filling of one higher surgery. So one thing you can say even before even analyzing anything about surgery coefficients is that if K has a constant, has any global surgeries, so let's just say Legendrian, then the smooth surgery coefficients, let's say it's smooth surgery coefficients corresponding to global concept surgery, global concept surgery. It's either empty, it doesn't have one, or it's all. So starting at some number, and moreover, that this sort of question here tells you that the surgery coefficient, even though that a priori, There's the Bennigan number could be very negative, or doing a positive contact surgery might correspond to negative smooth surgeries. This says that if the surgery is fillable, actually the smooth coefficient is positive also. So that, you know, it's a positive or non-negative number. So then it becomes interesting to try to figure out that smallest value is. So we can call it mu of A. So that's going to be either this P naught that's above, or it's called an intermediate. So what can you say about this mu? I think what I'm going to do is I'll just sort of state a basic fact about it, and then just do an example because the example is fun. Maybe I won't prove it now. So if mu of P is finite, then you can say a little bit about where it is. Now that between twice of the world in this. This but in general, it's not dependent on any sort of obvious topological quantities of they figured out the numbers before it's not. And so yes. But let me kind of finish the last three next to concrete example. Let's look at this. Because I think just turn out to the 2, 3, 7, 5. So let's see, what kind of John Stern kind of noticed about this, or one thing I noticed was that it had a lens space surgery. Back it's plus surgery on its lens space. And just for future reference, it's 4 wall genus is 5. Okay, so particularly we have total surgeries. We've already done. So you want to know maybe can you figure out what this mu is? What's the smallest fillable surgery? Well, like 18 is fillable. What about 17? So how would you see that? Well, if you know 18 surgery is fillable, then that corresponds to some there, like with the quality class, like over here, where 18 is the sum of the squares of the coefficient that's expressible. So if any of these ends are 1, then by positivity and negative, that means you sort of have the reverse of this picture. You have this intersecting one of these special spheres at 1, so you can blow it back down instead of surgery. So that's one big But you put a couple of threes into this formula, you'll be able to Fillable genus is 6, and it isn't. Okay, so in other words, in this expression, we had another one. So you get it from these. So finally, plus seconds. I mean, plus 16 surgery is not fillable. And well, one thing that is you can do a similar thing, but the thing when I code is in fact is due to topology. Yeah. That we look at it plus 15 surgery on this plus 1 does not have the negative of the full manifold. Okay, so if 16 surgery were fillable, this expression it would be expressed as a sum of squares like over there, but none of the numbers can be one because we want to get a filling of 15 surgery that would necessarily make it. So so there are a couple of ways to do that. I guess 16 is 4 squared. Where it is, where it is. These are also what we do wrong. So there's no way to read 16. It doesn't contradict something that also. Again,
this example died. This last 16 certainly the diagram.
it's no, just 16 should be have a tight structure. I believe so. I think. Yeah, I think everything above 9. We put it in the slides. Oh, that's right. Exactly. It's a well, yeah, it's oh, I think the one that they're able to provide a lot of examples and dependable structures.
That example has TD max minutes 1, right? And so like it's question about description, it's gonna take in something for this class about everything bigger than impressions.
Yeah. So that's interesting. So that was actually played earlier on taking out and there. So that's pretty cool on how to create fillable. If A is again these slides. That tells you that it bounds plenty of this as well. So it's not picture, but this earlier result was distracting. Sense about the implementation. But so another the Brownian slice have to have like there's a -1 location 0. But for us, say counted that it's likely just informal, that's not necessarily the case. So like A20 is positive on the size of that years. So as I scoop that out, you get a symplectically small zeros are green. But that goes to benefit -2, so that's not like +2 2. So we can say is that actually the Brownian slice is the same thing as quasi slice, quasi-object, and so this is their characterization of Fillable and plus 1 surgery. In our language, it would be to be smoothly sliced. So it's symplectically sliced and have a representative.